Now we will see one by one what are the user inputs for setting up reactions under the phase interaction panel. First, we input the total number of reactions that we want to model. That is here. We can increase or decrease it. Then we give the reaction name, which is given here. After this, we give the ID for reaction, that is here. This way, we can change the reactions. If we click on this ID, that particular reaction details will appear. This is to identify the reaction that we are editing. Then we specify number of reactants and number of products and all the details associated with that chemical reactions like phases, species that are participating, chemical species, stoichiometric coefficients, etc. All these details related to chemical reactions can be found here. So once all these user inputs are specified, we have defined the chemical reactions as part of the phase interactions. Let us now see how to define mass transfer. For defining mass transfer within the phase interaction panel, we click on Mass tab in the phase interaction panel. That is this particular tab. So all the details related to mass transfer will appear here. In order to set up the mass transfer or mass exchange between phases, we need to specify all these user inputs. First, we specify the number of mass transfer mechanisms, that is here. How many number of mechanisms of mass transfer or how many mass transfer reactions are going to be present, we define that number here. After this, we specify from which phase mass is going to be transferred and to which phase it is going to go. We define all that from phase and to phase here. That is, from phase is the phase from which mass is transferred out, to phase is the phase to which mass is transferred in. Then we select mechanisms for mass transfer. Various mechanisms are available like constant rate, cavitation, evaporation condensation, and user defined. Please note that constant rate is not applicable for VOF and cavitation is used only for mixture. So for VOF we mostly use user defined. Here we will see how surface tension is included for phase interaction in the CFD calculations. Now, as we know from our physics understanding that surface tension is a force that arises due to attractive molecular forces at interface fluids. Wherever there is interface between fluids, surface tension is acting. Surface tension coefficient is a parameter which is used for calculation of surface tension within the CFD model. We need to give the surface tension coefficient. It can be constant or a variable of, let's say, temperature. Now, this surface tension coefficient is used and it is multiplied by the sum of inverse curvature radii to calculate a pressure difference, which is then used in the CFD calculations. As you can see, if we have such type of an interface for 3D calculations, this is the pressure differential that is calculated from surface tension coefficient and the inverse of curvature radii. And for 2D calculations, it is in this way. That is just the surface tension coefficient divided by the radii of curvature. So this is how surface tension is included in the calculations. We need to give the surface tension coefficient. Within the phase interaction panel, there is a section or tab called surface tension. In this, the two phases which are modeled appear and we have to give surface tension coefficient here. It may be constant or a function of, let's say, some variable like temperature. It is usually in Newton per meter. Surface tension is present whenever interface exists between two different fluids. But how do we know that this surface tension value is important and we need to consider this in CFD calculations? There are some basic steps or calculations which will give us an idea of whether surface tension is a considerable force or not. First, we calculate the Reynolds number, which is given by the ratio of density, length scale, velocity divided by viscosity. After knowing the value of Reynolds number, we see if the Reynolds number value is less than 1 or greater than 1. If the Reynolds number is less than 1, we calculate the capillary number, which is given by this particular ratio. That is surface tension coefficient divided by the product of density, length scale and square of velocity. If Reynolds number on the other hand is greater than 1, we calculate the Weber number. The Weber number is given by this particular ratio. That is viscosity multiplied by velocity divided by the surface tension coefficient. Once we know the capillary number and the Weber number, if the Weber number is greater than 1 or the capillary number is less than 1, then surface tension is important and we need to consider surface tension in our calculations. Surface tension is modeled as an additional source term in the momentum equation. So whenever we give the surface tension coefficient, from that an additional source term is calculated and this is considered in the momentum equations in the CFD model. Next force or next interaction between phases is the wall adhesion. Wall adhesion arises because of cohesive forces between fluid and the surrounding wall. If we take the wall adhesion option in Fluent, it includes these wall adhesion cohesive forces between the fluid and surrounding wall. The wall adhesion forces are important because they play a major role in accurate prediction of meniscus shapes. So if we are modeling flows where there is an interface and it is in contact with wall, we need to consider wall adhesion forces. Whenever the interface is in touch with wall, we see wall adhesion forces playing a role and it is changing how the meniscus looks or behaves. This is the boundary condition panel for a wall and we can see wall adhesion option as a boundary condition. We need to give the contact angle for considering wall adhesion. We have to also include wall adhesion in the VOF multiphase panel before giving this contact angle. Let us see different solver settings that are applicable for the VOF model. First, we will discuss the solver settings for explicit solver. The first scheme is the pressure velocity coupling scheme. We select this in the solutions method panel within solutions. There are various options here as you can see. Generally, PISO is recommended for simple or non-complicated flows. Simple or simplic is used in case we are solving compressible flow or when the flows are solved in closed domain. Next parameter that we will discuss is the under relaxation factors. We can set them under solution control within the solution section. As you can see, the default values are shown here. They are very conservative in order to obtain better convergence. If the flow is simple, we can always increase these URFs in order to make the convergence quicker. You can notice that there is no URF for volume fraction because in explicit solver, VOF is solved explicitly within each subtime step. We use body force weighted option when there is a large presence of any body force in our calculation. This can be obtained in pressures in the spatial discretization schemes for pressure within the same solution method panel. For all other cases, we use the Presto scheme. For explicit solver, the volume fraction discretization schemes can also be selected. These can be selected in the solution method panel under the volume fraction spatial discretization schemes. First, we will discuss the geo reconstruct scheme. This is the default scheme. Its advantage is that there is very low or negligible numerical diffusion. It captures the curvature of the interface nicely. But for using the geo reconstruct, we need a very good quality mesh. Other scheme that we can use is CIC-SAM scheme. This is generally used for large mesh. The scheme is also very effective when we are using parallel solver. The next scheme is modified HRIC scheme, which can also be selected under the volume fraction discretization options. This is usually an alternative scheme and is used when neither of the above scheme works. Let us discuss the solver settings when we are using implicit solver. For implicit solver also, we have to select spatial discretization schemes for volume fraction within the solution method panel. It is recommended that with implicit solver, we use the modified HRIC scheme. You can notice that when we are using implicit solver, under the solution control section, under relaxation factor for volume fraction appears. So for implicit solver, we can also set the URF for volume fraction. Now we will discuss the operating conditions when we are using the VOF model. To set the operating conditions, we go to problem setup, cell zone conditions, and then click on operating conditions. That is, under the problem setup, we click on cell zone conditions. The number of cell zones that are present appear here. At the bottom, we have a button called operating conditions. Click on that, and then the operating condition panel pops up. As you can see, we can set the operating pressure here, we can set the reference pressure location, we can also click whether gravity is on or off, and we can set the magnitude and direction of gravity. We can also set the operating temperature for Boussinesq parameter, and also we can set a operating density. Now make a note that the reference pressure location should not be changed here. We keep as it is what appears by default. Here we specify the density, the lowest density of all the phases that are present. In case of compressible flow, we set the lowest density at the operating pressure. That is, if we are solving compressible flow, density may be a function of pressure also, and we set the lowest density at the operating pressure. We also specify the operating temperature for Boussinesq option if we have turned on the Boussinesq option. We specify gravity direction and magnitude here if the effect of gravitational force exists in our problem. Now let us quickly have a look at boundary conditions that we can give within the VOF model. For inlets, we can give velocity inlet, which is generally recommended for compressible flows. Now, as you already know how to set up the boundary conditions, we will only discuss the important user inputs related to the boundary conditions within the VOF model. So, for velocity inlet, you have to specify the velocity magnitude, the direction specification methods. You also have to input the turbulence parameters. Next is pressure inlet. For this, we enter the gauge total pressure and the direction specification method. Next inlet condition is mass flow inlets, in which we specify the mass flow rates. An important addition when we use the VOF model is the volume fraction input. This is given within the multiphase tab of the inlet boundary condition that we are using. So we specify the volume fraction of the phase that is entering here. We have to select phase within the boundary condition, and for that particular phase we enter the volume fraction. Next boundary condition is outlet. We will discuss the pressure outlet. Within the pressure outlet, we have to give the gauge pressure and the backflow volume fraction. Backflow volume fraction specifies the quantity or amount of the phase that will enter in case there is backflow at the outlet boundary condition. Outflow is also available, but it is incorrect for volume of fluid model. Note that outflow is not to be used with the VOF model. So we are ending this lecture here with a summary of what all we studied within this lecture. Initially we reviewed basics of the VOF model. After that we discussed in detail how to set up the VOF model within the CFD software Fluent. We studied all the steps one by one. After that we discussed in detail all the user inputs that are required to set up a VOF model. We discussed how to set up phase definitions. We discussed how to define all the parameters that are related to phase interactions. We discussed the implicit and explicit schemes as well as wall adhesion and surface tension inputs. At the end, we also discussed boundary conditions. So you are now familiar with all the user inputs that are needed for setting up the VOF model, how to give all those user inputs, and how to set up the entire VOF problem. So the next logical step would be for you to go through a tutorial which is based on the VOF model. After that, you will get a command of how to solve a problem within Fluent using the VOF model. Just a summary of all the references that were used for preparing these lectures. So we end this particular lecture on the VOF model. We would like to say thank you for watching this particular lecture. If you have any doubts, please contact us on our email address. So thank you for viewing this particular lecture within the advanced course of multiphase flow. See you in the next lecture.